Hello everyone, let's look at this problem. A projectile's motion after t seconds is given by these parametric equations. So the x component of the motion is v naught cos alpha t and y component of the motion is v naught sin alpha t minus half gt squared. Here v naught is the initial velocity and the projectile was released at angle alpha. So find vx and vy. So what are vx and vy? Vx is the x component of the velocity. So vx is dx by dt and vy is the y component of the velocity, which is dy by dt. I will first define x and y. It will help me later. So x equals to v naught cos alpha t. So control plus underscore to write a subscript 0. So v naught cos alpha times t, and y equals to v naught sin alpha t. I will give semicolon because I don't want to see the output. I just want to define them. V naught sin alpha t minus half gt squared. And then Vx will be Vx equals to the derivative of x with respect to t, and Vy will be the derivative of y with respect to t. And I want to see the output of these two inputs. So these are our Vx and Vy. Vx is v naught cos alpha and Vy is v naught sin alpha minus gt. Now alpha is equals to 45 degree and v naught is equals to 400 meter per second. So let's just define these two variables also. So alpha is equals to 45 degree. So to write degree, press escape button, write deg, and then again press the escape button, and v naught is equals to 400. So I just want to define them. It will help me later. And let's also define the value of g, which is 9.8. Now the first question is, when will the projectile hit the ground? So the ground is x-axis, and on the x-axis y is equals to 0. So we can set y equals to v naught sin alpha t minus half gt squared equals to 0 and find t. So let's solve. So we already have defined y, so y double equals to 0, and we want to know the time t. So we can see the projectile was at the ground at time t equals to 0, and the projectile will hit the ground at 57 seconds. Now the second question is, what is the maximum height reached by the projectile? So at maximum height, the y component of the velocity is 0. So we can say Vy equals to 0, and we can find the time. And using that time, we can find y. So y will be the maximum height. So let's solve Vy equals to 0. So at this time, t equals to 28 seconds, the y component of the velocity was 0. So using that time, we can find the value of y, and that y will be the maximum height. So we are replacing t with 28 seconds in the expression of y. So the value of y is 4081 meters or 4.081 kilometers. So this is the maximum height. Now let's look at the next question. So the next question is, how far from the starting point the projectile will hit the ground? So we already found the time when the projectile will hit the ground. We can just plug that t into x to find the value of x. So that will be the maximum horizontal distance covered by the projectile. So let's replace the t of x with t equals to 57 seconds. So this is the maximum distance, horizontal distance covered by the projectile, 16.3 kilometers. Now we have to plot the path of the projectile for v naught equals to 400 meter per second and alpha equals to 30 degree, 45 degree and 60 degree in a single graph. So you have to plot three parametric curves in a single graph for different angles. Now to plot the parametric curves, we have to give the range of t, and to get the full path we have to use the t where the projectile hit the ground, and we know that t for theta equals to 45 degree, alpha equals to 45 degree, but we don't know that t for alpha equals to 30 and 60 degree. We have to find that out. So let's just plot the first one for 30 degree. So parametric plot. So we have to use that expression x equals to v naught cos alpha t, and the y coordinate, the y component is v naught sin alpha t minus half gt squared. Now let's replace the alpha with 30 degree. And we already defined the v naught, so we don't have to change the v naught. But we need the range of t for 30 degree. So we need the t when the projectile hit the ground. So let's first find that out. So let's set x equals to 0 and find t. So alpha is 30 degree here. Well, I did a mistake. So at the ground x is not equals to 0, at the ground y is equals to 0. So you have to set y equals to 0 and find t for 30 degree. So alpha is 30 degree. So you can see at 40 seconds the projectile hit the ground. So you can use that range now from t from 0 to that 40 seconds. So this is the path of the projectile for alpha equals to 30 degree. Now we cannot add the curve of 45 degree in the same one because we have different ranges for there. So we have to use another parametric plot. So let's just set this a, and let's write b equals to, let's just copy paste this. So alpha will be 45 degree now, and we know the t for 45 degree at 57 seconds the projectile hit the ground. So if I use 57 seconds, we'll get the full path. Well, I did not change the second alpha. It should be 45 degree. Alright. So we can see that for theta equals to 45 degree, the maximum height was around 4,000 meters. Now let's do the same for alpha equals to 60 degree. So the time is 70 seconds. So we can do the same. C equals to parametric plot. We have to write. So you can just copy paste this. And then change the time t to 70 seconds. My cursor button is not working properly, so let's just write 70.696 here. I also have to change the angles. Angle is 60 degree here. So this is the path of the projectile for alpha equals to 60 degree. Now we have to show these three curves in a single graph. So we can use show function and write a, b, c inside show function, and that will do. Here we can see that there is a problem with the plot range, so we can fix that using the plot range function. So just write plot range and set it to full. So in that case you have to give a list and keep ABC inside the list and give the plot range option and set it to full. And now we can see the path of this three projectile. So the middle one is for alpha equals to 45 degrees, and the bottom one is for alpha equals to 30 degrees, and the top one is for alpha equals to 60 degrees. Well, we can use the drawing tools just to write 30, 45 and 60 degrees inside the graph. So let's just write that. This one is 30 degree. This one is 45 degrees. And the top one is 60 degrees. Let's look at another problem now. A quantum particle has this initial wave function. So this is a function, this is a piecewise function. So the wave function psi at x0, 0 is the time here, so this is the initial condition. So the position of the particle is defined by this piecewise function. So for x from 0 to a by 2, the position of the particle is a sine pi x by a cubed, or a sine cubed pi x by a. For x from a to a by 2 to a, the position of the particle is a times a minus x, where a and small a are positive constants. So the first question is, use this normalizing condition to find the value of a. So what is this normalizing condition? So if you take the square of the wave function, you get the probability of finding that particle in a certain position, and if you integrate that from 0 to a, we will get 1, because from the piecewise function we can tell that the particle is definitely inside 0 to a, and if you add all the probabilities, we'll get 1. So let's define the piecewise function now. So let's write psi, escape button, psi, and again escape button. So psi of x Now we have to write piecewise, and inside the square bracket we have to write the expressions. So the first one, we have to give a list, and inside the list we can write a sine pi x by a cubed, and then write double end sign, and give the range of x. So in that case the range of x is from 0 to a by 2. Then give a comma, and in the another list we'll give the other expression, a times a minus x double end, and the range is from a by 2 to a. We also kept the two lists inside another list. Well, in that case I think for piecewise we can't use double end, we have to give a comma there only. So write the expression, give a comma, and write the condition. So the piecewise functions gets defined. So the value of the function is 0 outside that range. So 0 means outside that range the value of the function is 0. Now we have to find the integral of psi function from 0 to a, and we have to find two integrals, and then we can just add them. The one is for 0 to a by 2, and the another one is for a by 2 to a. So let's write the expression. So the first one is from 0 to a by 2, and we have to take the square of the first expression, a sine cube pi x by a. And we have to take the square of it, dx, plus from a by 2 to a, and then the second expression is a times a minus x dx. And now we can solve the equation. We can set it equals to 1 and solve and find the value of a. So we have to take the square of the second expression as well. So you can keep this inside the solve and set it equals to 1. Also we can give the condition capital A and small a is greater than 0. So just write double end, and capital A is greater or equals to 0, and again double end, and write small a is greater or equals to 0. And we only want to know the value of a. So if you press shift enter now, we have got the value of a, and it will be in terms of small a. Now we have to graph the psi function for a equals to 3, small a equals to 3. So let's just define small a is equals to 3, And we also have to define capital A. So the capital A is this, so I have to copy paste this. Now both the value of capital A and small a are now in numerical. Now I can easily plot the function. So just write chi of x inside plot, and the range of x is from 0 to a. So you can directly plot piecewise function like this. So this is the plot of chi of x. So there is a discontinuity here, so don't worry about that. So this is the wave function of a quantum particle.